Last week in Chapter 11, we focused on the electronic structure of atoms. As I mentioned in the introduction to the last chapter, it's what's on the outside that counts. It's how the atoms look that's important. So our goal was to determine how the electrons are arranged in levels in the atom, because it's the electrons that are on the outermost level that determine the chemical properties of an atom. It tells us what kind of ion they'll form, what other elements they will want to bond with. In Chapter 3 and in Chapter 12, to continue that, we're going to be studying chemical compounds. We're going to learn how to look at the periodic table, pick two elements out, and you guys will be able to tell me exactly what chemical compound they're going to form. You're probably thinking now, my God, how would I do that? But by the time we're done with Chapter 3, I can point to, say, aluminum and iodine on the periodic table, and you'll be able to tell me the chemical formula for aluminum iodide. It's actually very logical. If you understand what we learned in Chapter 11 about electronic configurations, and I'm going to give you guys some more information, more detail now about the periodic table. We sort of introduced that in Chapter 2. Now I'm going to give you some more details about how you can use the periodic table to predict what various elements are going to do. So let's go ahead and get started on Chapter 3. So let's talk for a few minutes about the different ways matter can be classified, and then we'll focus on the chemical compounds in Chapter 3. First, matter can be classified into two broad categories: pure substances or mixture. And a pure substance, of course, means it's only made of one thing. A mixture means there are two or more different materials simply blended together. The simplest example of a pure substance, as you can probably guess, is an element. Essentially, a pure substance means that the smallest component of the substance are all identical. So whatever the smallest unit of that particular substance is, all those units are the same. Oxygen is made of atoms of oxygen. Hydrogen is made of atoms of hydrogen. Iron is made of atoms of iron. So elements are sort of the obvious example of a pure substance. You might be more surprised to know that chemical compounds like water or salt or ammonia are also considered pure substances. You might think, well, wait a minute, isn't water a mixture of hydrogen and oxygen? No, it's not. Water is actually made of only one kind of unit, and that is a molecule of water. So if you have a glass of water, the entire glass is made of nothing but H2O molecules. If you have a container of salt, the salt is made up entirely of sodium chloride units. A tank of ammonia gas is made up of molecules of ammonia, NH3. So both elements and chemical compounds are examples of pure substances. Mixtures, as you can guess, mean there are things mixed together. And mixtures also come in two types. The first of those is a homogeneous mixture. To be homogeneous, it has two requirements. First of all, this mixture must be uniform, meaning it must have the same composition throughout. I'm going to show you guys a video I made in the lab here in just a couple of minutes, and we'll go into this in more detail. So you'll be able to recognize when a mixture is homogeneous. That's probably the most complicated part of this particular unit. So in addition to being uniform, the materials also have to be intimately mixed. That means that the smallest pieces of the material are blended together. When salt dissolves in water, the individual sodium and chloride ions are floating around along with the individual molecules of water. So the water has been broken down into its smallest unit, a molecule. The salt has been broken into its smallest units, the sodium and chloride ions. I'm going to give you some easy ways to recognize homogeneous mixtures in our video in just a couple of minutes. The other type of mixtures are heterogeneous mixtures, and those are easy to recognize. They're not uniform. You look at a pizza, does every part of the pizza look exactly the same? Of course not. Italian salad dressing. It's got oil and vinegar and lots of herbs and things floating around in it. It is clearly not homogeneous. The computer you're probably looking at right now while you watch this video, it doesn't look all the same. Every part of it isn't exactly the same. Clearly, it's not homogeneous either. So let's go ahead and take a look at that video that I made, and I'll take you through some examples of each of these 4 classifications and how you can identify them when we have our quiz on this material. We've been talking about classifying matter and the 4 different ways we can do that. So our 2 major categories were either mixtures or pure substances. In the pure substance category, that's a relatively easy one. There's 2 possibilities. One is if it's an element, because the definition of a pure substance is that the smallest unit of the substance is all identical. This is a piece of silicon, and it's made entirely of atoms of silicon. So silicon is a pure substance. This is a bottle of lead. A piece of lead is made entirely of atoms of lead. So lead is an element. It's also a pure substance. The same thing is true for chemical compounds. For example, here's a beaker of water. Now sometimes students will say, no, wait a minute, isn't water a mixture of hydrogen and oxygen? No, it's not actually. Water, the smallest piece of water that you can have is a single molecule of water. So the smallest unit in this beaker of water that is actually water is a single H2O molecule. So we consider water to be a pure substance because it consists of only one kind of building block, only one kind of molecule. If we were to break the water molecules into hydrogen and oxygen, it simply wouldn't be water anymore. Salt is a pure substance. It's a chemical compound. If you can give it a specific name or a chemical formula, then it's a compound. So sodium chloride, NaCl, that makes it a chemical compound. Baking soda is sodium hydrogen carbonate, NaHCO3. It's also a chemical compound. Now when you get into mixtures, things get a little more complicated, because with mixtures, it's not always obvious whether it's going to be a homogeneous mixture or a heterogeneous mixture. So let's take a look at a few examples and see how you can tell the difference. As I mentioned a little while ago, mixtures are either homogeneous or heterogeneous. To be homogeneous, there are 2 requirements. The first is that the substance must be uniformly mixed. For example, if I took a cup of sugar and a cup of salt and I put them in my blender and I blended it up very thoroughly and I took a spoonful out, I would probably find it's half sugar, half salt. I could take some from the top, the middle, the bottom, and I would get the same percentage. So I would say, okay, it seems to be uniformly mixed. But there's a second requirement, and that is for the substance to be intimately mixed. If you looked under a magnifying glass or a microscope, you would be able to see individual crystals of sugar and salt. In order for that mixture to be truly homogeneous, the individual molecules and ions have to be broken apart and blended together. And no matter how much you grind that up and blend it, that is never going to happen. So that mixture of salt and sugar, although it's reasonably homogeneous, it is not intimately mixed. Now, there's 3 rules you can follow that make it very simple. Mixtures of gases are always homogeneous mixtures. And the reason is very simple. If you look around the air in the room, it's individual molecules of nitrogen and oxygen. They've already been broken up into their smallest components and allowed to mix. You know, if you walk around the room or around town, you can breathe just as well wherever you go because it's 21% oxygen everywhere. An easy trick for determining when a mixture is homogeneous, if it's gases, or it also works for liquids, is if you shine a light through it, it will be invisible. When I shine this light, you can see the light hitting my hand, but you can't see the beam traveling through the air. The particles in the air are so tiny that the waves of light simply go around them. If something is heterogeneous, that means the particles have not been broken down to their smallest components, and in that case, the beam of light will hit it and it will bounce off. If I shine this light on the wall here, you can see that light because the photons of light are hitting the wall, bouncing off into your eyes. When I shine the light across the room here, you can't see that beam in front of me because there's nothing for the photons to hit and bounce off and enter your eyes. So gases are easy. Our rule will be a mixture of gases is always homogeneous. Now you might be thinking, now wait a minute, what about smoke? I mean, when there's smoke, you can see the light shining through it. That's because smoke is not entirely made of gases. There are particles floating around in there. So that's not really a mixture of just gases. Air is a mixture of only gases, which is why it is transparent. If you can, when you're out in the woods sometimes hiking and you see a shaft of sunlight coming down through the trees, the reason you can see that beam of light is because all the dust particles in the air are making the photons of light bounce off of them into your eyes. If you go into the woods after it's rained and the air's nice and clear, you never see those shafts of light because now there's no particles in the air to reflect them. Now we can apply the same rule for mixtures of liquids. For example, this beaker contains salt water. It has salt dissolved in water. It looks homogeneous, but if we want to be absolutely sure, all we have to do is shine our laser through it, and you can't see the laser inside the beaker because there's no particles large enough to cause the light to reflect. The sodium and chloride ions are simply too small. If I shine my light through some vinegar, which is a solution of acetic acid in water, we can't see the beam. That tells us that's a homogeneous mixture. Same thing with 7-Up. If I shine the light through this bottle of 7-Up, I can't see the beam. Which means even though 7-Up has a lot of things in it, there's high fructose corn syrup, citric acid, potassium citrate, calcium disodium EDTA, a lot of chemicals in there, but they're clearly homogeneously mixed because it's transparent. Now, milk is something that gets hotly debated even in our department. Some chemistry teachers will tell you milk is homogeneous because it says it on the bottle, but it doesn't really say homogeneous, it says homogenized milk. When the milk comes out of the cow, it's not very uniform, and so they run it through a fancy blender to break up all the droplets of fat so that the milk will not separate into cream and skimmed milk. If I take just a little bit of milk here, I'm going to put that into my beaker. So just a few drops of milk. We'll stir that up. And now let's shine the laser through that little teeny bit of milk in there. And lo and behold, look at that. You can see that beam perfectly illuminated. That's because there are particles in the milk, particles of fat and protein, which are not completely broken down to individual molecules, and therefore they block the light. So my personal perspective is milk is not really homogeneous. It is uniform, yes, but we haven't broken it down into its tiniest particles. I don't consider that to be intimately mixed. Now, some of my colleagues will say milk is homogeneous because if you look at it, it looks homogeneous. And so that's really a matter of personal opinion. If you're taking a quiz from me, you better say milk is heterogeneous. Maybe one of my colleagues, they'll tell you it's homogeneous. That's what you better write on their quizzes. Now let's take a close-up look of our laser test just so you can see it a bit better. We'll start out with just a beaker of pure water. And if we shine our laser through there, you notice you cannot see the beam. We know the beam is passing through because you can see it hitting my hand, but it's not visible in the pure water because water molecules are simply too small to cause the photons of light to bounce off. Let's go ahead now and add a little bit of milk. We'll put maybe a dropper of milk in here. Go ahead and stir that around. And you can see already it looks a little bit hazy there. Let's shine our laser through this now. And wow, you can really see the beam of light traveling through there. It's still coming through and hitting my hand, but I can see the beam very nicely in there as it passes through. The particles of fat and protein in the milk are simply large enough that they cause the photons of light to bounce off. If we could break them up into individual fat molecules, then milk would be completely transparent. That would be rather weird. So the laser is a very handy way to be able to detect whether liquids are homogeneous or not. And that brings us to mixtures of solids. And yes, you can have mixtures that are solid. For example, this is a piece of brass, and brass is an alloy of copper and zinc. To make brass, they melt copper and zinc, allow the atoms to mix together uniformly and intimately, and then when it cools, you have this nice homogeneous mixture of the two metals. Gold, like in a gold ring, my ring is made of 14 karat gold. That means it's about 60% gold. They usually put silver or palladium or copper, some other metal in there. And the reason they do that is not because they're cheap, it's because pure gold is very soft. And if you made a ring out of pure gold, you could simply squish it flat. So they alloy the gold with other metals in order to make it stronger. So 14 karat gold, that's an alloy. Therefore, it's a homogeneous mixture. Brass is an alloy of copper and zinc, homogeneous mixture. Stainless steel, like your silverware, is made with iron and chromium. That's a homogeneous mixture. So just to summarize, it's relatively straightforward. Gases are easy. Mixtures of gases are always homogeneous. So if that comes up on a quiz and it's a mixture of gases, you know what to write down. Liquid mixtures, it depends. When it's a mixture of liquids, it depends on whether it is transparent or not. If we've got salt water, the light passes right through it. It looks homogeneous, and it actually is. If you look at my beaker with a little bit of milk in here, it's a little bit hazy, but we shine the laser through. Well, if I can get there we go. We can see that beam nicely illuminated inside the beaker. Now you won't always have a laser, so I'll try to make sure that everything is fairly, straightforward on a quiz. But in a pinch, that's a simple way to tell. You might wonder whether 7-Up is homogeneous. The laser test said it was. And then finally, we just talked about metals. So for solid mixtures, the only common example of a solid mixture that's homogeneous is if it's an alloy. Now you're probably thinking, gosh, on a quiz, how am I going to know if something is an alloy? Well, very simple answer. If I call it an alloy in the question, if I say bronze, an alloy of copper and tin, you're going to go, alloy, I think I'd better write down homogeneous mixture, and you'd be absolutely right. So it's relatively straightforward. Now, how do you recognize a heterogeneous mixture? Very simple. It's not homogeneous. There are a lot of heterogeneous mixtures. Most mixtures are heterogeneous. My lab coat, this laser pointer, the computer, all those things are heterogeneous. To be homogeneous, it has to be uniform. Every part of it has to look exactly the same. That computer certainly doesn't look homogeneous. This box is clearly not homogeneous. So most mixtures, the vast majority, are heterogeneous mixtures. So to make your life easy, all you have to do is figure out when it's homogeneous. And if it's not homogeneous, by default, it must be heterogeneous. In chapters 2 and 11, we learned all about atoms and elements. So we're going to take the next step now in chapters 3 and 12 and learn all about chemical compounds. First, we're going to need some definitions. So what exactly is a chemical compound? It's nothing more than atoms of two or more different elements bonded together. And they're held together by what we call chemical bonds. So what the heck is a chemical bond? And that is the topic of these two chapters. In chapter 3, we're going to learn all about a type of bond called ionic bonds, and then in Chapter 12 we will discuss what are known as covalent bonds. Why do atoms form bonds in the first place? What drives them to want to do this? And the answer is pretty simple. They want to become more stable, or I often say in class that they want to be happier. So the elements are trying to become as happy as they can be, and most elements on the periodic table are not happy. They are not as stable as they could be, and they can become stable or happy, if we care to say it that way, by forming chemical bonds with other elements. What is it that makes an atom stable? What do they want to get? A few of the atoms on the periodic table are stable just as they are. They do not want to react with anything, and we'll talk about that in a little while. But what is it that they have that the other atoms don't have? And that is the right number of what we call valence electrons. Valence electrons are simply the electrons in the outermost energy level that actually has electrons in it. Of course, there's an infinite number of energy levels, but if you look at the farthest one out that's actually occupied, that has electrons in it, there's a certain magic number of electrons that all elements want to have in that outer level. If they have that to start with, they're good. They don't want to react with anything. If they don't have that right number of electrons, then their goal is to change that. They want to change the number of electrons they have so that they can become like these other elements that are already happy. Let's take a look back at some of these diagrams we did for elements in Chapter 11. The valence electron in hydrogen is this one here because it's the outermost occupied level, and it has one electron in it. So a hydrogen atom has one valence electron. Helium has 2 electrons in its outermost occupied level, so it's got 2 valence electrons. If we go back to the beginning of period number 2 with lithium, lithium has only 1 valence electron. These 2 electrons here are in an internal or an inside level. Valence electrons only look at the ones in the outermost occupied level. So lithium and hydrogen actually have that in common. They each have 1 valence electron. Beryllium has 2 electrons in the second level, so it's got 2 valence electrons. Boron has 1, 2, 3 valence electrons. And if we jump all the way over to the end of the second period to neon, neon has got 8 electrons in the second energy level. It has 8 valence electrons. So this is one way we could determine the number of valence electrons in an atom, but it would be very time consuming. We're going to have to come up with an easier way to do this. If we take a look back at the electronic configurations that we did in Chapter 11, after we did those circle diagrams, we said, well, we can make it a little bit easier, and we could write out these electronic configurations, and that's another way we can determine how many valence electrons there are. For example, if we look at hydrogen, lithium, sodium, and potassium, what they all have in common is they've got 1 electron in the outermost energy level. If you look at it, they're also all members of group 1, so gosh, the group number 1 also is the number of valence electrons. You might think that's a coincidence, but it's not. Let's take a look at beryllium. Beryllium has 2 valence electrons. There's 2 in the outermost level, and it's a member of group 2. If we went down through all the remaining members of group 2, they would all end with S2. Magnesium would end with 3s2, calcium with 4s2, radium with 7s2. That's what they all have in common. Experiment number 7, which we did last week, deals with that. We were studying the reactions of the elements in group 2 and noticed that they did have similar reactions with each other, and now we know why. It's because they have the same number of valence electrons. Now, take a look at boron. You might think, oh, boron's only got one valence electron, but that's not true. It has one in the outermost subshell, but we're interested in the entire energy level. So boron has 1, 2, 3 valence electrons, and it is in group 3, also known as group 13. In the newer terminology, we use numbers from just 1 through 18, but all we have to do is look at the second digit. So the 3 or the 3 still tells us it has 3 valence electrons. Carbon has 1, 2, 3, 4 in group 4. Nitrogen has 5 in group 5. Oxygen has a total of 6 in group 6. Fluorine has 7, and it's in group 7. And argon and neon both have 8, and they are in group 8. Helium is the one oddball here. Even though helium is sitting over in group 8, it doesn't actually have 8 valence electrons. Helium is there, as we've talked about before, because its properties are very similar to these other elements. And the reason the properties are similar is pretty straightforward. If you look at helium, it has 2 electrons in the first energy level, which means level number 1 is completely full. Neon has 8 electrons in the second energy level. It also has a completely filled energy level. Having a completely full energy level makes an atom very stable. And that's why helium and neon have similar properties. That is, they're very unreactive. They don't like to react with other elements. There's an even simpler way to represent the valence electrons in an atom, and that's called a Lewis electron dot diagram. In a Lewis diagram, we basically represent each valence electron as a dot. So we'll start out with hydrogen. Hydrogen's in group number 1. It has 1 valence electron, so we simply put 1 dot next to hydrogen. This is going to come in very handy in chapter 12 when we talk about covalent bonding, because we're literally going to be connecting the dots between different atoms. If we go on to helium on the other side here, helium, although it's in group 8, of course we've already decided, it only has 2 electrons, so helium's electron dot diagram shows 2 dots. Back to the beginning of the second period, lithium in group 1, 1 valence electron. Beryllium in group 2 has 2 valence electrons. Now, if I were lecturing to you guys live, I would just keep going on, and I would wait until somebody got so uncomfortable that they had to finally ask me why the dots are separate in beryllium, but they're together in helium. But since I don't have you in front of me here, I'm going to assume you're all wondering that, and I'm going to answer that question. Electrons, as we've talked about before, don't like each other. They like to stay as far from one another as they can. In the first energy level, there's only a single subshell, and that's the 1s subshell. And in that subshell, there's only a single orbital, that 1s orbital. So the 2 electrons in helium have to share that orbital. That's why we're showing them together here. They're like sharing the bed there in the electron hotel. When we get to period number 2, we have an s and a p subshell, which means we have an s orbital and 3 p orbitals. That's a total of 4 orbitals in which the electrons can reside. So the electrons are not going to want to share an orbital if there's an open one available. In beryllium, when that second electron comes in, if the first electron has taken residence in the 2s orbital, that next electron is going to say, well, gee, there's 3 empty p orbitals. I think I'll go stay in one of those. Why would I want to share a bed with the other electron when I can have my own? Same thing happens with boron. With its 3 valence electrons and 4 orbitals, they spread out. Carbon has 4 valence electrons, but there are 4 orbitals. They each take 1 orbital. Now we get to group number 5. Nitrogen has 5 valence electrons, but only 4 orbitals, so at this point, we're going to have to pair them up. It's very important, though, if you're doing one of these electron dot diagrams on a quiz, you don't want to pair them up until you have at least 5. So for the first 4, they all go in single, then you get a pair. For example, you would not want to make, say, 2 pairs of dots and 1 single on nitrogen. That would be incorrect. You couldn't put 2 pairs on carbon, or 1 pair and 2 singles. It has to be 4 separate electrons. If we move on to oxygen with its 6 valence electrons, we have 2 pairs and 2 singles. And we get to fluorine with its 7 electrons. We've got 3 pairs and 1 single electron. And finally, we make it to neon. Neon has 8 valence electrons, and that is enough electrons to completely fill that second energy level, which is why, as I said earlier, helium and neon happen to be very stable elements. As early as the late 1800s, chemists recognized that the elements in group 8 on the periodic table were particularly stable. It was very difficult, if not impossible, to get any of them to undergo chemical reactions. And they found that they all had one thing in common, at least all of them except helium, and that is each one had 8 valence electrons. From neon all the way down group 8, each of the elements had this 8 valence electrons, and that turned out to be a very stable arrangement. Helium, as we mentioned earlier, is stable for a simple reason, and that is its outermost level is completely full. Same thing is true with neon. That is the best situation if you can do that. Argon through radon, although they don't have completely filled outer energy levels because they've got D and or F subshells in lower levels that still remain unfilled, there seems to be something particularly stable about having 8 valence electrons. And a little over 100 years ago, chemists, recognizing that, came up with something called the octet rule. And the octet rule basically says any element that has 8 valence electrons will be particularly stable. Now, the other elements on the periodic table wish they could be like these noble gases in group 8. They would love nothing more than to become one of those elements. So, for example, what would fluorine have to do to become neon? And the answer, of course, that most students come up with is fluorine would need to gain an electron. Most every student I ask this question to says, well, if fluorine gained an electron, it would be neon. Well, it hasn't become neon. It looks like neon. You know, from the outside, yeah, a little makeup here, and fluorine looks a heck of a lot like neon. They would be hard to tell apart. But to truly become neon, what would fluorine have to do? And the answer, of course, it would have to gain a proton. Neon is element number 10, fluorine is element number 9. If you want to change fluorine into neon, you would have to somehow put an extra proton into that nucleus, and that is simply something that cannot happen in a chemical reaction. It would take a nuclear process. It's not impossible, but it's beyond the realm of chemical reactions. So there's no way that fluorine can actually become neon. So what's the next best thing? And that would be if it could look like neon. If fluorine could look like neon, it would feel pretty good about itself. I imagine that a lot of you have either done this or you know people that have. You buy fancy shoes or clothes, you get your hair done certain ways because there's someone out there who's famous and you admire them or you're envious of them. You think, man, I wish I could be that person. Well, you can't, but the next best thing is maybe you could look like that person. And I'm certainly not putting any of you down because I must admit in my youth I was guilty of that same thing. 1975, Sean Connery, who was James Bond before that, came out with a movie, The Man Who Would Be King, and I was a huge Sean Connery fan, so I saw all of his movies. And so in 1976, I decided I would grow these big mutton chop sideburns, and you can probably tell there's quite an amazing resemblance there. Well, maybe not that amazing. So, like fluorine, I couldn't be Sean Connery, but I could try to at least emulate him a little bit.
So atoms, even though they can't become a different element, they want to look like them, and they do that by obtaining this octet of electrons. So how do they go about doing that? Let's take a look at lithium, for example. Lithium has two options to become like a noble gas. It could lose one electron and drop back to having two, and it would look like helium. It could gain 7 electrons, and it could look like neon. Now, human nature, being like atomic nature, if you had a choice of getting what you wanted the easy way or the hard way, most people would choose the easy way. And lithium says, you know what, losing 1 sounds a heck of a lot easier than gaining 7. So that's exactly what lithium does. It loses 1 electron, and now it has a positive charge because it's lost that electron, but it now has a total of 2 valence electrons, just like helium. It's now become a lithium ion, and it is very stable because it is now isoelectronic with helium. Isoelectronic simply means having the same electronic configuration. That's what all the other elements in the other groups want to do. Beryllium has the option of losing 2 or gaining 6. No surprise, it loses 2 and gets a positive 2 charge. Boron's 2 options are to lose 3 or gain 5, and of course it elects to lose 3 because it's the shorter route back to the noble gases. So the lithium, beryllium, and boron ions are all now isoelectronic with helium because they have the same electronic configuration. Carbon, unfortunately, is sort of out of luck. Carbon needs to either lose 4 or gain 4, and there's no way it can do that. It turns out that 4 electrons is just too many. It is too difficult to gain 4 electrons, and it takes too much energy to remove 4 electrons from an atom. So carbon is not going to form an ion by itself. There's no such thing as a C4 plus or a C4 minus ion. Doesn't mean carbon is doomed. We're going to get to carbon in the next chapter. Carbon will manage to get its octet by sharing electrons rather than becoming an ion. If we move on to nitrogen, for nitrogen, it's a shorter route to move ahead and gain electrons. If nitrogen gains 3 electrons, it will now be isoelectronic to neon, and it has its octet, but because it gained 3 electrons, it's got a negative 3 charge. Oxygen, of course, finds it easier to gain 2 than lose 8, and so it ends up with a negative 2 charge, and fluorine finds gaining 1 much preferable to losing 7, and now the fluorine has also become isoelectronic with neon. Each of the elements in groups 1, 2, 3, and 5, 6, and 7, this is what they want to do in chemical reactions. As you go down each of these groups, they'll do the same thing because everybody in the group has the same electron dot diagram to start with, and therefore they're going to want to do the same thing in their chemical reactions. Let's go ahead and look and see now how each of these elements accomplishes their goal. We'll start out with lithium. We'll go back to our circle diagrams that we used back in chapter 11. Lithium has this 1 valence electron, and it would love to get rid of it because if it does, it will only have 2 electrons in the first level, and it will look just like helium. The problem is lithium can't just cough up an electron like a cat coughs up a hairball. If you have a car that you want to sell, you have to have a buyer. If there's no buyer, then you're stuck. So lithium needs to find somebody that would like an electron. So who might be a good possible partner for lithium? Who might want an electron? The answer that most people come up with is fluorine. Fluorine's a good choice. We know that fluorine on the other side of the periodic table just needs 1 more electron to fill its octet and become isoelectronic with neon. If a lithium atom bumps into a fluorine atom, immediately that electron from lithium's second energy level will come in and it will fill fluorine's second energy level. The lithium has now become a lithium ion, and the fluorine becomes a fluoride ion. So lithium lost the electron and became positive. Fluorine gained an electron and became negative. Now, both of these atoms are particularly happy. They've got the number of electrons they want to have. So what do they do next? Do they simply go on their merry way, or do they stay together? And the answer is they absolutely stay together. Because the ions have opposite charges, they are immediately attracted to each other, and they will come together to form a chemical compound. And we call this chemical compound lithium fluoride. The naming rules for ionic compounds is pretty simple. The positive ion, its name simply stays the way it was, but for the negative ion, we just change the ending to "ide." If we said lithium fluorine, people might think we just had some lithium and some fluorine. If we say lithium fluoride, they go, oh, you mean the ion that fluorine turned into. And that is important. You've probably heard of fluoride before. They put that in toothpaste and drinking water, and fluoride's good. It gets incorporated into your tooth enamel, and it protects your teeth from decay. You would not want to put fluorine in toothpaste or in drinking water. Fluorine is one of the most dangerous substances there is. That element is so reactive it eats through almost anything. Very nasty stuff. And it's very reactive because it's dying to get that extra electron. But once the fluorine gets that electron, whew, I'm happy as a clam now. I look just like neon. So fluoride ions are actually very inert, which is why they're excellent at protecting your teeth from decay. Because this compound consists of two ions, it's logical that we call it an ionic compound. In Chapter 3, we're going to be focusing completely on ionic compounds. When we get to Chapter 12 next week, we're going to change our focus and talk all about covalent compounds. Those are the ones that I mentioned about carbon and how carbon will share electrons. That's where covalent compounds come from. The term covalent means like co as in sharing and valent, valence electrons. Now, could you think of anybody else that might make a good partner for lithium? And you'll probably say, oh, gee, how about chlorine? How about bromine? You're thinking inside the box and you're just working your way down group 7. Well, could an element from a different group bond with lithium? Absolutely. For example, could lithium bond with oxygen? At first glance, you might wonder how that could work out, because oxygen needs 2 more electrons. Will oxygen be sort of happy to get 1 electron? Not at all. For elements, it is all or nothing. Getting an extra electron does not help. It's got to have the 2, but lithium can only give 1. Easy way around that? Let's simply bring in 2 atoms of lithium. There's no rule that says you have to have 1 atom of each element in a chemical compound. If that were the case, there wouldn't be very many chemical compounds. So if 2 lithium atoms come in contact with an oxygen atom, they will each give 1 of their electrons to the oxygen. And now each lithium atom becomes a lithium ion, and the oxygen becomes what we call an oxide ion. Remember that when an element becomes a negative ion, we change that ending. And so the formula for our new compound will be Li2O. The 2 tells us that there are 2 lithium ions, and we simply call it lithium oxide. Now some people wonder, well, shouldn't we call it dilithium oxide because there's 2 of them? And we don't have to do that. There's a simple reason we don't do it. How many different combinations could you come up with of lithium and oxide ions in which the positive and negative charges balanced? Could we have 3 lithiums and 1 oxide? Wouldn't work. 1 lithium and 1 oxide? Nope. It has to be 2 and 1. So there's only 1 possible compound that you can make between lithium ions and oxide ions. So we don't have to tell people there are 2 lithiums. We don't have to say dilithium oxide. If we say lithium oxide, a chemist would say, oh, you mean the one and only lithium oxide. Now we definitely don't want to go to all the trouble of drawing complicated diagrams every time we need to figure out the formula for an ionic compound. So let me show you a much simpler stepwise process that you can follow. Suppose we wanted to come up with the formula for the compound magnesium fluoride. The first step is to simply figure out what the symbols are for the two elements. Make sure you look in the objectives in our course packet, because there's a list of about 31 elements that you guys need to learn. And so be sure you work on that before we get to the next quiz and exam. In this case, our symbols are Mg and F for magnesium and fluorine. Second step, we want to determine the charges for each ion, and that's what we just did, of course. We went through and figured out that magnesium being in group 2 would be a positive 2, and fluoride being in group 7 would be a negative 1. So now we have the symbol of each element and we know their charges. Our third step is simply to balance the charges. That is the absolute unbreakable rule when it comes to ionic compounds. If you remember nothing else, remember this. The pluses have to equal the minuses. So to make that happen, we're going to need 2 fluoride ions to go with our 1 magnesium. That will give us 2 pluses and 2 minuses. And then we simply put those together to write our formula. So 1 magnesium and 2 fluorides, it's simply going to be MgF2. This is the procedure you'll use anytime you have the name of an ionic compound and you want to change that into a chemical formula. Write down the symbols, determine their charges from the group that they're in, figure out how many of each ion you need to make sure the pluses and minuses equal, and then put the compound together. Let's take a look at another example, sodium nitride. So sodium is Na, nitrogen is N, that's our first step. We want to determine the charges. Sodium is in group 1, it will be a +1. Nitrogen is in group 5, which means it will be a -3. To balance these, since the nitride is a -3, we would need 3 sodiums to balance out the charges, and therefore our chemical formula is simply Na3N. The subscript always applies to whichever element it follows. There's only 1 nitrogen. It's not necessary to put the 1 in. We just assume if there's no subscript, it must be 1. It's like H2O. 2 H's and 1 O. We don't call it H2O1. That's not necessary. Let's take a look at another one. Aluminum sulfide. Of course, that must consist of aluminum and sulfur. I'm not going to write out the steps anymore. I think by now, hopefully, you know those or you've written them down in your notes. So these are our 2 elements. Aluminum is in group 3. It's going to have a +3 charge. Sulfur is in group 6. It's going to have a -2 charge. Now this one's a little more complicated because of this odd-even combination. This sometimes gives students a little bit of trouble. 2 sulfides would be too many negatives, but 1 is not enough. So we're going to use a trick like you guys have used in math since elementary school, and that is to find a common multiple for 2 and 3. And of course, what do 2 and 3 both go into equally? And that would be 6. If we could get 6 pluses and 6 minuses, then our charges would balance. So to get 6 pluses, we would need 2 aluminum ions, and to get 6 minuses, we would need 3 sulfide ions. To check our work, we just want to make sure that the plus column equals the minus column. If it does, then we should have a viable ionic compound, and we can simply write a formula to reflect 2 aluminum and 3 sulfurs. That would be the chemical formula then for aluminum sulfide. As you should remember from chapter 2, the periodic table is divided into 2 parts. The elements to the right of this black staircase are nonmetals, and all these elements to the left are metals, with the exception of hydrogen. Hydrogen you can sort of think of as sitting right over here. If you take a look at the table, you can see that most of the elements on the table are actually metals, and only a small number are nonmetals. The nonmetals, of course, are very important because most living things are composed mostly of nonmetals. Our compounds, if you look at the formulas of each of the ionic compounds that we've looked at so far, they all have one thing in common. Every one of them has a metal and a nonmetal. So there's always an element from the left of the staircase and one from the right. That is normal for ionic compounds. It is very rare to have an ionic compound that does not consist of both metals and nonmetals. And that makes it an easy way to recognize whether you have an ionic compound or not. That's going to become important pretty soon, because when we do the names of chemical compounds, the rules for ionic compounds are different than those for covalent compounds, and so you'll have to be able to tell them apart. We learned earlier that the charges of the ions in each group can be determined from the group number. So in group number 1, they all have one valence electron, which they want to lose. They get a charge of +1. If you're in group 2, they want to lose their 2 valence electrons, and they all have a charge of +2. And in group 3, they want to lose their 3 valence electrons and get a charge of +3. We skipped carbon because we determined that 4 electrons was simply too many to gain or lose, so we'll come back to carbon next week. When we get over to nitrogen in group 5, it's actually quicker or shorter to move forward and gain 3 electrons, making the elements in this group a -3. Oxygen and the members of group 6 gain 2 electrons and become -2, and the elements in group 7 will gain 1 electron and have a charge of -1. So the elements in the S and the P block are very predictable. There are some exceptions, but we're probably going to avoid those just to keep things from becoming too complicated. So in general, we can predict the charge of any ion from groups 1, 2, and 3, and 5, 6, and 7. Now what happens when we move into the D block, these elements in the middle? They do have group numbers, but I can tell you right now those group numbers aren't going to be very helpful. We can't actually predict what the charges are going to be for elements in the D block. I refer to the S and the P block elements as the well-behaved elements because they tend to follow the rules. That's not, unfortunately, the case in the D block. We have 2 problems in the D block. One, like I just said, is the group number doesn't really tell you anything about the charge. The fact that nickel is in group 10, it doesn't mean it's going to have a charge of 10. So we cannot simply look at the table like we were able to do in the S and the P block. Our second problem is that the metals in the D block can actually form ions of different charges. For example, nickel can have a charge of +2 or +4. That, of course, has nothing to do with the number 10. Gold can be a +1 or a +3. You cannot get that information from the periodic table, so we have to find another way to determine that information. Let's consider an example of iron and chlorine. Iron and chlorine form 2 different compounds, FeCl2 and FeCl3. If we were going to name those using our rules that we've learned, FeCl2 would simply be iron chloride. Just like we did with the S and P block elements, the first element we just used the name, and the second element we changed the ending to "ide." Now if we were to name the second compound, the first part of the name would be iron, and the last part would again be chloride. That's a real problem. Can these 2 compounds have the same name? If I ask the folks in the stockroom for a bottle of iron chloride, when they go and look, they're going to find 2 different chemicals. Does it matter which one they bring me? Absolutely. They can have totally different properties. So when we get into the D block, when there's more than one possible compound, we need to add something else to the name. If I had two students with the same first and last name, I would probably use their middle name or middle initial to distinguish between the two. We're going to do sort of the same thing here. What we do with ionic compounds in the D block, and it also applies to the F block, is we're going to add something in between the iron and the chloride. And what we're going to add is a Roman numeral. That Roman numeral tells us what the charge is on the iron ion. And you're probably wondering, well, how do you know the charge when you can't get it from the group number? This 8 up here certainly isn't the same as a 2. It's rather simple, actually. We know two things. Number one, we know that in any ionic compound, the pluses have to equal the minuses, and we always know the minuses. A chloride ion is always -1. So 2 chlorides add up to -2. Therefore, the iron would have to have a +2 charge to balance it out, and thus iron Roman numeral 2 chloride tells us that the iron in this particular compound has a charge of +2. In the second one, there are 3 chlorides, which adds up to -3, so the iron in this case, of course, would have to have a +3 charge, and this is called iron 3 chloride. Whenever we're in the D block or in the F block, we have to make sure that we include that Roman numeral, since there's more than one possible combination that you can have with the metal and the nonmetal. In the S and the P block, things were easier because there was only one possibility, so we didn't need to be any more specific. Let's go ahead and work some practice problems using some metals from the D block. So for our first one, Ag2O. Good thing to start with when you're getting the hang of this initially is to write down a list of all the atoms. So we can see that there are 2 atoms of silver and 1 atom of oxygen in the compound. We need to know the charge on the silver in order to figure out the Roman numeral, so we'll get that from the charge on oxygen. Oxygen, of course, is in group 6, therefore it's going to have a -2 charge. To balance that out, each silver ion would have to have a +1 charge. If we check our totals here, of course, we get 2 pluses and 2 minuses. As long as the charges are balanced, we should be good. And so the name of the compound is simply silver 1 oxide. Again, the 1 refers to the charge, not how many atoms there are. That's a common mistake students make. Let's take a look at another one. In this case, we have 1 atom of nickel and 4 atoms of bromine. Bromine is in group 7, and therefore bromide will have a charge of -1. That's 4 negatives, so the nickel would have to be a +4 to balance it out, and our plus column once again equals our minus column. The name of the compound then would simply be nickel 4 bromide, again the 4 referring to the charge on the nickel. Now this is a little more complicated one because there's more than one of each element. That always makes things a little more challenging. So again, let's start by listing our atoms. We have 3 atoms of chromium and 4 phosphorus. Phosphorus is in group 5, so it's a -3 charge. So we have 4 -3s. That's going to add up to 12. So each chromium would need to have a +4 charge to balance that out. We end up then with 12 pluses in the plus column, 12 minuses in the minus column, and therefore it would be chromium 4 phosphide. Doesn't matter that we have 3 chromiums, that 4 says each of those has a charge of +4. Now let's try working some problems in the opposite direction, where I give you a name and you come up with the formula. Copper 2 arsenide. We'll do this the same way we did the ones with metals in the S and the P block. So our first step is to simply write down the symbols for the elements. So Cu for copper, As for arsenic. We then want to include the charges, so the Roman numeral makes it very easy. We don't even need to worry about group numbers. That Roman numeral 2 immediately tells us that copper is a +2. Arsenic, being in group 5, of course, will be a -3. We need to figure out how we can balance the charges. And again, this is one of those odd-even combinations that can be, excuse me, a little challenging. So we want to find that common multiple, which in this case, again, will be 6. So to get 6 pluses, we're going to need 3 of the copper ions. To get 6 minuses, we'll need 2 of the arsenide ions. Our pluses and minuses balance, that's important. And all we have to do then is put those together, and that gives us the formula for copper 2 arsenide. Next up, let's take a look at tungsten 6 sulfide. Tungsten is W over here, number 74, and sulfide, of course, is sulfur. We know the charge on the tungsten. We have Roman numeral 6, so it will be a 6+. Sulfur is in group 6 on the periodic table, therefore it's a 2-. To make things balance out, we would of course need 3 of our sulfides to equal the charge on the tungsten, which gives us 6 pluses in the plus column and 6 minuses in the minus column. And therefore our formula is simply WS3. Let's do one more example. Mercury 1 nitride. Mercury is Hg, so it's one of those elements where the symbol doesn't seem to match the name. That's because the symbol is based on the Latin name hygrorgyrum. But we use the name mercury, that's our modern name for it. So mercury is Hg, and nitride is N. The Roman numeral 1, of course, tells us that mercury has a charge of +1, and nitride, being in group 5, would have a -3. So it looks like we would need 3 mercuries to equal the charge on 1 nitride. We've got 3 pluses and 3 minuses, and therefore our formula will simply be Hg3n. There's a different class of ions which are called polyatomic ions. All of the ions we've been looking at so far are monatomic, and of course mono means one, atomic means atom. So a monatomic ion is simply a single atom with a charge. Things like a magnesium ion or a nitride ion, all the ions we've been looking at so far are all monatomic ions. They're formed when an atom either gains or loses electrons. A polyatomic ion is one that contains more than one atom. So it's a group of atoms that also has a positive or negative charge. Most polyatomic ions have negative charges. It's rare for one to have a positive charge. The ammonium ion here, that's the only example that you will run across in our class of a polyatomic ion with a positive charge. We're going to learn a whole bunch of them, like the carbonate ion, that have negative charges. Luckily, the polyatomic ions tend to fall into families. There's going to be a total of 39 of these, and that probably sounds like a huge task to learn 39 different polyatomic ions. But the good news is 36 of those 39 fall into 5 families. So if you learn the head of each of those 5 families, it's pretty simple to figure out the formulas for all of the family members. And even better, you don't even have to memorize the 5 heads of the families, because I'm going to teach you a very simple little memory trick that will make it easy to remember those. So don't get overly concerned here as we get started, because I'm going to make it, I think, relatively straightforward as we go along. So let's start out with the carbon family. Carbon forms an ion with oxygen. In fact, most of the polyatomic ions we'll be looking at consist of an element from the non-metals in the table plus one or more atoms of oxygen bonded to it. The reason that they have charges is because normally the first atom, in this case the carbon, just doesn't have enough electrons to satisfy all those oxygens. If you think about it, how many electrons does an oxygen atom want to gain to get its octet? And that, of course, would be 2. So 3 oxygens would need a total of 6 electrons to satisfy their octet, but carbon, being in group 4, only has 4. That means we have a deficit of 2 electrons, and so they have to borrow a couple of extra electrons. And we don't worry about right now where they borrow them from, clearly from some other element. But they have to somehow get those extra 2 electrons so that there's enough for the 3 oxygens. The 4 from carbon and the 2 from they borrowed are enough to provide the 6 needed. Naming polyatomic ions is also pretty straightforward. We just begin with the name of the first atom in the formula, carbon, and we add the ending -ate. So carbonate simply means a carbon atom connected to some oxygen atoms. Now, how do we know that it's going to be 3? Well, that little memory tool that I promised to tell you about will be coming up later on, and I'll show you how it's real easy to know that carbonate atoms have 3 oxygens. It's also easy to remember that they have a -2 charge. Now, the heads of the families can be changed into other ions. Some can have more flexibility than others. The one thing that carbon can do is you can add a hydrogen atom to a carbonate. Whenever you add a hydrogen atom to a polyatomic ion, it always decreases the charge by 1. And the reason for that is the hydrogen itself brings an electron to the party. Hydrogen has 1 valence electron. Carbon has 4, so that's 5. If the 3 oxygens need 6, we only need to borrow 1 electron. The names are also very straightforward. All we do is just add the word hydrogen in front of the name. Now, there's an old-fashioned terminology that we use sometimes. Instead of writing hydrogen, sometimes you'll see it written as bicarbonate. If you bought baking soda, it says sodium bicarbonate on the box. The prefix bi is just an old-fashioned name that means the same as hydrogen. So either one of those is perfectly fine. That's essentially the entire carbon family. It's a pretty small family here, sort of like a single parent with 1 child. Some of the families get very large. So let's move from carbon next door to nitrogen. Nitrogen atoms also like to bond with 3 oxygens. But because the nitrogen comes in with 5 electrons, they only need to borrow 1 extra electron to satisfy all the oxygens. To name it, it's simply called a nitrate ion. So nit for nitrogen, and then ate tells us it's attached to some oxygens. And again, in a little while, I'll show you my very fun memory tool that will let you know that. Now, you can't add a hydrogen to a nitrate ion for a very simple reason. If we added a hydrogen to it, that negative charge would disappear. It's not that we can't do it. If we do that, though, it will no longer be a polyatomic ion. If you add an H to the nitrate, it becomes a neutral chemical compound. That's a topic for another chapter in the future. So we'll only add hydrogens to polyatomic ions if they have at least a -2 charge or greater. However, there is a second thing that one can do to polyatomic ions, and that is we can remove an oxygen. The rule is very simple. When you remove an oxygen from a polyatomic ion, the charge remains the same. And it'll be clearer why that's the case when we get into the next chapter. In chapter 12, we'll be drawing 3-dimensional pictures of the various polyatomic ions. Now, we can't also call this a nitrate ion. We have to somehow distinguish the two. So whenever you remove an oxygen, we simply change the ending from ate to ite. And that makes up the nitrogen family, also a pretty small family. Let's move on over now to phosphorus. So we're going to take a right turn here in the periodic table and take a look at phosphorus. We're not going to have polyatomic ions with oxygen as the first element, because the element at the beginning has to share its electrons with the oxygens, and oxygens don't like sharing. Same thing with fluorine. You'd never find fluorine in the middle sharing a bunch of electrons with other atoms. These two guys do not like to share. So we'll go down into the third period and take a look at phosphorus. It turns out that phosphorus likes to bond with 4 oxygens to make a polyatomic ion. And again, we can use our little math trick. 4 oxygens would need 8 electrons. Phosphorus only has 5. That leaves a deficit of 3, thus the -3 charge. And we simply call this a phosphate ion. So phosphorus becomes phosphate. Because it has a charge of -3, we can definitely add a hydrogen to it, and that will reduce the charge by 1, and we'll simply add the word hydrogen to the front of the name. With phosphate, because of its larger charge, we can even add another hydrogen to it and reduce the charge even further. To tell people that there are 2 hydrogens, we add the prefix di in front of it, so it becomes dihydrogen phosphate. 2 hydrogens and a phosphate. We can also do the little oxygen switch as well. We can take a phosphate and remove an oxygen. That leaves the charge the same, but now the name will change. Now it becomes phosphite. Anytime we remove an oxygen, 8 becomes ite. We can then do the same things we did here with our phosphite. We can add 1 hydrogen to it and make a hydrogen phosphite ion. We can add a second hydrogen to it, and we can make a dihydrogen phosphite ion. So at this point, from that single parent, the phosphate ion, we now have 6 different possibilities. But as they always say on those TV infomercials, but wait, there's more. There's a third thing that you can do with many polyatomic ions, and that is we can switch out the first atom with another member of the family. For example, phosphorus and arsenic have very similar properties. So arsenic makes the same polyatomic ions that phosphorus does. We can put an arsenic in the phosphate, and it simply becomes arsenate. We can add a hydrogen and make it into hydrogen arsenate. We can add a second hydrogen and make it dihydrogen arsenate. We can do the same thing with the arsenates that we did with the phosphate, and that is remove an oxygen. So we can change arsenate into arsenite by removing an oxygen. We can also do the same thing with the hydrogens. If we add 1 hydrogen, we get the hydrogen arsenite, and if we add a second hydrogen, we get dihydrogen arsenite. So at this point, we've gone through 3 of our families. If you know carbonate, nitrate, and phosphate, the big 3, that's now a total of 16 polyatomic ions that you can figure out by either adding hydrogens, removing oxygens, or switching out the first element with a member of its family. Let's move on then from phosphorus over to sulfur. Sulfur likes to bond with 4 oxygens. And of course, if sulfur has 6 valence electrons and the 4 oxygens need 8, that means we have a shortage of 2, thus the -2 charge. So sulfur becomes sulfate. Because it has a -2 charge, of course, we can add a hydrogen to it, and we can make it into hydrogen sulfate. We won't want to add another hydrogen, however, because that would eliminate the negative charge entirely, and it would no longer be a polyatomic ion, which is the topic for today. We can, however, remove an oxygen. So we can take an oxygen away from sulfate and make that into sulfite. We could also add a hydrogen to the sulfite and make it into hydrogen sulfite. So there's 4 different possibilities from the sulfur family, but we're not done yet. We can also replace the sulfur with selenium, the next member of its group. If we put a selenium atom in there, it now becomes selenate. We can add a hydrogen to it and make it hydrogen selenate. We can remove an oxygen and turn it into selenite, and then we can add a hydrogen to that one, and we'll make it hydrogen selenite. So the sulfur has 8 members of its family. So now with the carbonate, the nitrate, the phosphate, and the sulfate, those big 4, we have a total of 24 different variations that we can figure out. Finally, we're going to finish up with the chlorine family. So chlorine likes to bond with 3 oxygens. Now chlorine is the one instance where doing that little math doesn't work out, because chlorine has 7 valence electrons. Oxygen only needs 6, so you wouldn't think we would need to borrow. But chlorine doesn't exactly follow those rules. Chlorine's simply not willing to share all 7. Even though it's got 7, it says, nope, sorry oxygen, I'll share 5, you're going to have to go borrow 1. So this becomes the chlorate ion. Now we can't add hydrogen to chlorate because it only has a -1 charge, but we can remove an oxygen. And if we do that, it becomes chlorite. Now the chlorine family can do something that the others don't, and that is we can even remove another oxygen. So we'll have to come up with another name. You might think, well, could we call it chlorote? Chlorute? No, we don't do any of those things. We call this hypochlorite. The prefix hypo means below or less. For example, if a hypodermic needle means it goes below the dermis, below the skin. If someone is hypoglycemic, they have low blood sugar. So hypochlorite simply means less than chlorite or below chlorite. The chlorate can also do another interesting thing, and that is we can add another oxygen to it. And if hypo means less, of course, what means more? Hyper. Somewhere in history, I don't know where it happened, the hyper was shortened to just per. So we don't actually call it hyperchlorate, it's simply called perchlorate. Now, as we did with sulfur and phosphorus, we can also swap out family members. So the chlorine can be replaced by bromine. And we can make a bromate ion, a bromite, a hypobromite, and of course, a perbromate. In this family, we can even go down to iodine and do the same thing again. So we can make an iodate and an iodite and a hypoiodite and finally a periodate. The chlorine family adds another 12 to our total. So between the carbonate, nitrate, phosphate, sulfate, and chlorate families, we have a total of 36 variations. I mentioned before that you would need to know a total of 39 polyatomic ions. That takes care of 36 of them. The really good news is in a few minutes, I'm going to show you an extremely easy way to memorize the big 5, the carbonate, nitrate, phosphate, sulfate, and chlorate. So that'll be very simple. But we still are missing 3 ions. There's 3 left to go. I refer to those as the orphan ions because they stand alone. They have no family members. They are just individual ions, and those 3 you will just have to memorize. The first one, OH-, is called a hydroxide ion. That's a very common ion. When we get into chapter 5, we're going to talk a lot about hydroxide ions. We have this one known as an acetate ion. It is in acetic acid, which makes up vinegar. And finally, one I mentioned briefly earlier is the ammonium ion. It is the one positive polyatomic ion that we're going to talk about in Chemistry 3A. Positive polyatomic ions are not very common. There are thousands of the negative ions, but only a handful of the positive ones. So that's something you may get into more if you go as far as, say, organic chemistry. At this point, then, we have our 39 polyatomic ions. We have the 36 that are members of the 5 families, plus the 3 orphans. That gives us our total of 39. I promised you earlier that I would show you an easy way to remember the big 5 polyatomic ions are the heads of the family, and my friend Nick here is going to help us do that. This little memory phrase is going to tell us the formulas of each of the 5 main polyatomic ions. A student of mine many years ago named Rudy found this on the internet somewhere and shared it with me, and I thought it was a very clever idea. So let's figure out how this little memory phrase will give us the big 5 ions. Each ion or each word that's in capital letters here represents one of the big 5: nitrate, carbonate, chlorate, sulfate, and phosphate. The way we figure out the formula is very straightforward. The N tells us it's nitrogen. The number of consonants in the word, in this case it's 1, 2, 3, tells us the number of oxygens, and the number of vowels tells us what the charge is. So it's very simple to figure out nitrate. N, 3 consonants, 3 oxygens. I, we have 1 vowel, -1 charge. If we move to camel for carbonate, there are 1, 2, 3 consonants, thus 3 oxygens. 2 vowels means a -2 charge. Clam for chlorate, we have 1, 2, 3 consonants, thus 3 oxygens. 1 vowel, -1 charge. Supper for sulfate, there are 1, 2, 3, 4 consonants, thus 4 oxygens, and there are 2 vowels, giving it a -2 charge. And finally, Phoenix gives us phosphate. We have 1, 2, 3, 4 consonants for our 4 oxygens, 1, 2, 3 vowels, a -3 charge. It's a very handy way to learn the big 5 polyatomic ions. Once you know those, then you can make the changes. You can remove an oxygen, add a hydrogen, switch out a family member, and you can come up with a total then of 36 different polyatomic ions. So let's work through some sample problems using polyatomic ions. We're going to do this essentially the same as we did with the regular monatomic ions, and that is basically we need to write down the symbol and the charge of the ions and then simply balance those charges. So we have aluminum, which is in group 3, so it's a +3 charge. Nitrate, which you're going to learn from Nick in Nick the Camel, has a -1 charge. So to balance this out, we're going to need 3 nitrates to go with the 1 aluminum. That'll be 3 minuses and 1 +3. It's important to keep in mind that the 3 subscript here in the nitrate has nothing to do with the charge. The 3 simply tells us how many oxygens we have, so the negative sign applies to the entire ion. The NO3 unit has a -1 charge. Now you're probably wondering, why did I put the nitrate in parentheses? Well, you have to do that because we want the 3 to apply to the whole thing. We wouldn't want to just write NO33. It's NO3 times 3. Okay, FeBrO2 in parentheses 2, that parentheses again tells us there are 2 of this polyatomic ion. The Fe is easy, we know that's iron, but what's this guy called? Well, it's called bromite. Now, again, you don't have to actually memorize the bromite because it can be figured out. If you know that bromine is part of the chlorine family, that tells us, oh, it must be related to the chlorate, which is the head of that family. Now, how could we get from ClO3 to BrO2? Well, the first thing we might do is to swap out that first element. So, well, we want to go from chlorine to bromine, so let's make that switch. And that's going to change our name from chlorate to bromate. So we're getting closer, but we also need to lose an oxygen. So let's take an oxygen away from this bromate, and lo and behold, it's now become the bromite. You really don't have to memorize the bromite ion because it can be figured out from the chlorate. If bromite has a -1 charge, and there are two of them, that adds up to -2. That means the iron would have to have a +2 charge to balance it out, and thus our compound would be iron 2 bromite. Gold 3 sulfite. Gold is element number 79, so that's Au. And the Roman numeral 3, of course, immediately tells us that it has a charge of +3. The polyatomic ions, of course, you're going to learn, and sulfite is SO3 2-. This is another one of those even-odd combinations, so we're going to go with the common multiple of 6 again. So to get 6 positive charges, we would need 2 gold ions. To get 6 negatives, we would need 3 sulfite ions. So the formula would have to have 2 golds and 3 sulfites. That would give us 2 positive 3s for 6 pluses and 3 negative 2s for 6 minuses. VOH5, V is vanadium over here, element number 23. So we know the first part of the name is vanadium. And OH is one of our orphan ions, one of those polyatomic ions. That is the hydroxide ion. Hydroxide ions have a charge of -1. And since there are 5 of them, that means we have a total of 5 negatives. So the vanadium would have to have a +5 charge to balance that out. And thus it will be vanadium 5 hydroxide, with the 5 telling us that's the charge on the vanadium. Ammonium phosphate, I threw in 2 polyatomic ions in this one, so you'll have to learn those, of course. Ammonium is NH4+, and phosphate is PO4 3-. Since this is a -3 and ammonium's a +1, we would need 3 ammoniums to balance out the charge on that single phosphate ion. So it'd be NH4 parentheses 3 PO4. In this chapter, we've been dealing almost exclusively with ionic compounds. When we get to chapter 12 next week, we'll start talking about covalent compounds. I'm just going to give you sort of a brief introduction here in how to name those, so that since we've been doing the naming rules for ionic compounds, covalent compounds are actually very simple compared to ionic compounds. So it'll be pretty easy to add that into our list. Covalent compounds are made of nonmetals. Ionic compounds invariably consist of a metal and a nonmetal. Covalent compounds consist totally of nonmetals. That's an easy way to recognize them. Covalent compounds can form more than one substance from the same element, sort of like the metals in the D block. We had FeCl2 and FeCl3. In covalent compounds, the same kind of thing happens. You can have more than one combination of the same elements. You may remember way back to chapter 2, that represents what was called the law of multiple proportions. So we're going to be using a series of prefixes, and we're going to use just the ones that go from 1 up to 8. Some of these you'll be familiar with, and some maybe not so much. Mono means 1. Di is 2. Tri, like a tricycle, is 3. Tetra for 4. Penta for 5, like the Pentagon is a 5-sided building. That's why they call it the Pentagon. Hex or hexa for 6. Hepta for 7. And octa for 8. You've heard of an octopus before. They have 8 legs. That's where we use that prefix. When you're naming a covalent compound, it's pretty simple. However many atoms of a particular element are present in the compound, you just insert the appropriate prefix in the front of it. For example, CO is commonly known as carbon monoxide. Now, the prefix mono is optional. If we don't have a prefix in there, we just assume it's 1. You'll notice I didn't call this monocarbon monoxide. In fact, the mon isn't really necessary unless it's just been called that forever. Carbon monoxide's name has been around for a long, long time, long before we came up with these official naming rules, so some names are simply grandfathered in. We keep those names because they've always been called that, but normally the prefix mono isn't commonly used. There's also, of course, carbon and 2 oxygens, and that is known as carbon dioxide. So we do need to put the di in there. So carbon monoxide has 1 O, carbon dioxide has 2. If you have more than one of each element, then you'll need to use 2 prefixes. For example, P2S5 is diphosphorus pentasulfide, so 2 phosphorus, 5 sulfur. One thing I should mention, you'll notice that when I did carbon monoxide, we left off the O there because monooxide would be a little redundant. Because oxygen begins with a vowel, we normally leave off the vowel. For example, if you had 4 oxygens, you wouldn't call it tetraoxide. We would normally just call it tetroxide. If the second element ends with begins with a consonant, then we go ahead and leave it as it is. Let's wrap things up by just summarizing the naming rules for our various types of compounds. The first type of compound we talked about were ionic compounds that contained a metal from the S or the P block. These are the simplest ones. In those cases, all you do is simply name the 2 ions in the substance. So if we have a compound with lithium and phosphate, since lithium is in the S block, we just name the 2 ions, and it's called lithium phosphate. No Roman numerals, no prefixes. Students love to put prefixes in ionic compounds. Don't do that. Do not call this trilithium phosphate. That is a very common mistake. Only use the prefixes if it is a covalent compound. Our second type of compound were ionic compounds with D or F block metals. In that case, we add a Roman numeral to the name so that we know what the charge is on the metal. So in this case, we have copper and acetate. Acetate has a charge of -1, and there are 2 of them. So that's a -2. That means the copper, of course, would have to have a +2 charge, and thus it would be copper 2 acetate. The third type of compound we just talked about were covalent compounds. With covalent compounds, we use our prefixes. We wouldn't use a Roman numeral because covalent compounds don't have charges. But because there are more than one possibility, there's Cl2O, Cl2O5, even Cl2O7. There's a number of different compounds of chlorine and oxygen. We have to tell people which one this one is. So this compound is simply dichlorine trioxide. Di for 2 chlorines and tri for 3 oxides.
That wraps up everything for Chapter 3. So in Chapter 3, this is usually one of the more difficult chapters for students. They tend to have a lot of trouble with the name, especially with the naming compounds and writing chemical formulas. So you want to make sure that you practice that. So by the end of chapter 3, we should know how to name and write formulas of ionic compounds, both using elements in the S and P block and also using the transition metals in the D block, which require Roman numerals. You should also know how to name and write the formulas for covalent compounds, which use the prefixes like di, tri, tetra, so on and so forth. There's a nice handout in the course packet that has all the rules for naming ionic and covalent compounds and discusses some examples that you can practice on. In chapter 12, we're going to move on into covalent compounds. We're going to learn how to put together atoms that are sharing electrons rather than exchanging electrons. And we're going to take it further and figure out how to draw three-dimensional pictures of these molecules and figure out what the angles are between the atoms. So let's go ahead and move on in to chapter 12.